Hi, Mark Brezinski. This is a lecture that I have sort of dreaded giving, and it should have probably been earlier in the tutorial series, but the problem is we're looking at the OCT embodiments, time domain OCT, swept source OCT, and spectral radar or Fourier domain OCT, which is a crappy name because they're all Fourier domain. But the problem is that from physics and engineering standpoint, it's going to be too basic, and from a clinical standpoint, it's not easy. This is a purely classical presentation. I'm not going to take into account quantum noise. That will be covered in the next talk, most likely the next talk, which will be the quantum field approach to OCT, which we've already published, but I'll do in YouTube video format. So again, we're going to be treating this classically. And the biggest issues between these modalities is acquisition rate and noise. And noise doesn't seem that significant, but noise comes down to how you can penetrate. And the signal to noise ratio or the dynamic range, how well you see contrast and how well you penetrate. And we're only going to touch on some of this stuff. And I don't want you to think that I'm biased toward one versus the other. We have two SS-OCT systems, and they're commercial, Thor Labs and Light Labs. And we tend to, they're great for applications. But we have a breadboard system that's predominantly a time domain OCT system, but we do switch it over to a swept source OCT system at times. And we will in the experiment shown at the end of this, toward the end of the talk. So first of all, one thing that's sort of a killer is, I get this a lot, particularly from the ophthalmology community, is that SSOCT has a superior resolution to TD-OCT, time domain OCT, and that is not true. It's so if we look at delta L, it's the coherence length, but let's just use it to represent resolution. It's dependent on the median wavelength and the bandwidth of the source in free space with a Gaussian distribution and no dispersion. Those were the qualifiers, but that's how it's always assessed. So why is it that if I go to my local optometrist, he's got a time, or she has a time domain system, and it's got crappy images, and you see these swept source with great images. They're better, in my opinion. It's all down to better engineering, because this may or may not be the reason, but let me just give you, for those who weren't involved in OCT from early on, the swept source started to arise around the late 1990s, but time domain OCT was relatively patent protected. SS-OCT, its concept has been around since the Michelson-Morley experiments from the 19th century, late 19th century. It was part of relativity. So it was not patent protected. So a lot more engineering, in my opinion, has gone into SSOCT than has gone into time domain OCT. And what the ultimate limit of time domain OCT, and it has its challenges bringing it up to the same acquisition rate, we don't really know yet. Again, my name is Mark Brezinski. You've seen this list before if you've seen my videos. Just the last line, between 2000 and 2010, it didn't seem like people were taking into account the noise levels and the problem with A to D conversion with SS OCT. And so uh, so we published numerous papers on that, which I'm going to discuss. But I want to point out a lot of groups in the early 2000 published papers on SSOCT, improving the optoelectronics and making this better. And I actually wonder if we hadn't pushed so hard for non-transparent tissue, particularly cardiology, where we needed this speed, whether SSOCT would have even arisen very much at all, whether time domain OCT would have been the standard if ophthalmology was the only clinical embodiment. And I'll try to explain that a little bit in a minute. Now, this book I wrote back in 2006, and chapters 1 through 4 will give you the basic physics behind OCT. Chapters 5 through 11 are advanced OCT theory, which I'm going to go through in the next slide. Chapters 5 and 7, you pretty much the whole chapter there, it's going to go bounce between time domain and the other two embodiments. And then in chapter 6 on optoelectronics, the relevant area, this page is 158 to 160. And there was something on one of the sites for the book in 2006, from 2006, which I'll tell you why I haven't written a second edition in a moment. But there was only 2 comments that didn't get 5 stars. The one said there were a lot of typos, which is absolutely true. I only had half the book written when they already started selling it, and I rushed through it, and there are typos. But the second one said that in 2006 the book was outdated because SSOCT was developed afterwards. Well, SSOCT was developed in the 1990s and then a large part of the book deals with SSOCT. Now, the reason why I haven't written a second edition is I'm not sure how much I would change. What's really changed, is there are advances in the optoelectronics, and if you're an engineer, you would really love that. But these chapters with the physics, nothing's changed, so they wouldn't be any different. The initial chapters are still the same on theory, and then when you get to the clinical chapters, first, the applications have not moved as fast as I would like. I mean, the lack of double-blind clinical trials or clinical trials that tell us anything about morbidity and mortality as a whole is really discouraging. And there's just not a lot to write in a new book. But all right, so let's get back on track again. So we're going to picture the light emitted from our source as being a pulse with an envelope and a carrier frequency. So it's really the carrier frequency, and that carrier frequency has an envelope, and the detector can only pick up the whole core envelope. It's not quick enough in most systems. I'm not talking about phase sensitive, a special type of OCT, to pick up the rest of the signal. Now, if you go back to the axial resolution lecture, most OCT sources are not pulsatile like this. They're CW, constant wave, and they have like a fingerprint that's over which the beam is constant. But that's explained in the axial resolution section, and I don't want to go back to that right now. If for those interested, go back to axial resolution. And we're not going to be dealing with lateral resolution at all because it's really not affected to a significant degree by any of them. Only the CCD and spectral radar, and we're not going to get into that kind of detail here. So classical, I just want to mention that classical interference occurs in an OCT system when the path lengths in each arm match to within the coherence length. And OCT measures the interference, and and not actually the back reflection. And let me make that more clear. I think in retrospect I should have switched these two slides. But so all OCT systems for the or all essentially all OCT systems use this type of interferometer, Michelson interferometer. In time domain, that reference arm changes its length, and in the spectral, it stays constant. So you have a light source, and with time domain and spectral radar, um, it's uh, it's just a low coherence source with SSOCT. You know, the frequency is swept, and so why do you need this? Why do you need a reference arm? And for some people, sorry, this is a little bit basic. So with ultrasound, we measure the distances. Let's go to the next slide first for a second. So we want to make out this layers. We're imaging through a mesenteric artery. I think this is the celiac artery. Straight through, and we want to make out the layers. And with ultrasound, we would just measure back reflection intensity at different levels by the time of flight. The problem is the speed of light. So light goes around the Earth. I've never calculated this myself, 4 times in a second. But so if you think about the fact the resolution of OCT is 10 microns, that's pretty hard to do with electronics. It's impossible to do with straight electronics like you can with ultrasound. So what you do is you interfere it with itself. And for classical, we say that the light wave interferes with itself. In quantum mechanics, you're going to see that that does not hold. A photon interferes with itself. So we want to collect, with time domain, we're going to, in a single A scan, collect backscattering data as a function of depth, analogous to ultrasound. With the other two techniques, we're just going to take the entire A scan and measure all the frequencies, and then we'll see what we do with that later. But that's the difference. So SS-OCT is not like analogous to ultrasound. Now these are drawings of schematics of the 3 OCT systems. I'm not going into them. Time domain, for what we're concerned about, is the only one with moving parts. The reference arm changes. There's a mirror, and we assume there's a mirror in the reference arm. And these have gotten more complicated with time, but again, this is the kind of changes that have occurred since 2006, and there's no real reason for us to discuss that. Now, understanding Fourier relationships is critical in understanding OCT, other than thinking it's just ultrasound with light. And it's important for the understanding how it measures, has a high axial resolution, but it also tells us how we differentiate the 3 types. Now, this is one of the only formulas I'm going to give you for people with a physics background, or sorry. But so what happens is, and I'm going to show this pictorially. So if we look at the right, that's the amplitude is a function of time. That little f was a function of time. And what this equation is saying is we can add up a bunch of frequencies and their phases to get that amplitude. So if it's a square wave, a sinusoidal wave, a Gaussian wave, a Poisson wave or pulse, then there's a certain frequencies, which is what capital FV, the V is the frequency distribution for our purposes here, that would give it that to us. And the reverse holds. If we want, for a given frequency distribution, we can take the Fourier transform of the amplitude, and it'll tell us what frequencies are in that configuration. And I know that's a little bit confusing, and this is derived out in the first 4 chapters of the textbook and hopefully made much more simpler. So let's take a, this is actually a mathematical relationship, but it holds in real life too, but this would hold for a variety of things, not just light. So let's just say on the left, we have a square pulse coming into our detector. So it's got a flat amplitude. It just rapidly starts up. It's got a constant amplitude and then it drops off. Well, what frequencies need to add up to give us that? So we do the Fourier transform and we get the frequency distribution on the right. And so the time domain SSOCT is measuring the left. SSOCT is measuring the right. And then it's important to understand it's trying to convert it. It's deriving indirectly the left. What we want is the left. So time domain is actually measuring what we want to. And we're deriving from the frequency spectrum in SSOCT and spectral radar what we want. The back reflection intensity is a function of depth. Now, we generally use Gaussian sources because the Fourier transform of a Gaussian source is Gaussian. So there's no side lobes. And that becomes important when we plot. And the statistics of all our sources are going to be Bose-Einstein statistics, giving us Gaussian waveforms. Even though we're using a laser, there's a reason why these aren't Poisson distributions. But so we want a nice little curve like that fits into a pixel that we can plot. So pixels that have back reflection, we don't want them to have side lobes, which I didn't show you an example of, but a lot of frequency distributions will give you side lobes that will leak into another pixel and then that just causes additional noise. So let's get to the OCT embodiments. So let's start off with time domain. So again, it's like ultrasound. Now, in the most ancient system, when we started this whole thing back in the early 90s, we used a mirror to change the optical path length in the reference arm. And remember, so the light's coming out of our source, and we're saying it's pulsatile and Gaussian shaped, and it's split to the reference in the sample, and it bounces off someplace. It's bouncing off from within the sample and off the mirror in the reference arm. So why do we need to move the reference arm mirror? So what happens is that each length position the reference arm is in, that's where you're sampling from within the sample. I wish I said that better. So if we look at the picture on the left of our artery, the red arrow would be one mirror position. And when the mirror is the same optical length as where that red arrow is pointing to, you're only getting data from there. And then when the mirror is in the position, optical distance of the yellow arrow, you're only getting data from the yellow arrow. So the two arms only interfere. So when the reference mirror is close to the beam splitter, we're getting more information from the surface because that's the optical path lengths are equal in both arms. And when we have the mirror farther in, we're getting deeper information when the path length is longer in that reference arm. Now, we run into a problem, and this is the big challenge with time domain OCT. Okay, there's a limit, which is pretty slow, how much you can move a mirror back and forth. You can calculate this out, the weight of a mirror, things you can use to move the mirror. And you're not going to get more, this is going to isn't going to image more than a frame per second. And there's tilting mirrors, there's stretching the path length with a piezoelectric crystal that expands and contracts, grading-based delay line. And there were more advanced designs, but sort of the design stopped when people started using SSOCT. So we really don't know how good we can get, I don't believe, with time domain. Because I just, all the focus went to spectral domain. And this is what a plot coming toward the detector would look like with time domain OCT. So we see two peaks in our sample. Okay, and those two peaks represent back reflection. And this came, I'm fortunate to these authors. This was on the internet, but citing the authors. And the mirror is in different positions from peak 1 and peak 2. So now, let's go to swept source or spectral radar. And I'm predominant, swept source, you're sweeping the laser. So at any one time, you theoretically have almost a monochromatic wave on the sample, and you're sweeping through the same bandwidth that you used in time domain. It's just you're doing it over sweeping across the frequencies. I'm going to explain it in terms of more spectral domain. So let's just say we're firing the whole bandwidth down into our interferometer. It gets split. It goes to bounces off the mirror and bounces from within the sample. Now you get interference. But the interference that's being measured here is not, but you're getting the interference now from everywhere. And what we're looking at is the frequency distribution within one A scan. So remember, a B scan is two-dimensional and A scan is one scan. So the distribution of frequencies in that, all the back reflection coming back at once. Okay, no moving mirror in either side, so we don't have to worry about increasing speed that way. So this is very fast, and so what's done is, so the left shows not a pulse, not two peaks. It shows a distribution of the intensity of various frequencies. And then a fast Fourier transform, or a Fourier transform, is performed, and you get the two peaks. That sounds really great, except the Fourier transform isn't performed in mid-air before it hits the detector. The Fourier transform is performed in the computer. Now, but that leaves us with a lot of problems. And we're going to get into that. That moving mirror in time domain created a Doppler shift that got us above the noise. But we're going to run into problems with things like we have to digitize the signal to get it into the computer. So the optical signal and the signal in the electronics is initially analog. It's continuous, but we need it digitized into bits for the computer. And with these spectral techniques, we're going to run into a problem. So the dynamic range and signal to noise ratio affect your ability to see structure. If you lose it, then if it's reduced, you lose penetration and you lose contrast. And there's a difference between penetration and imaging penetration. So light penetrates very far. The light from the OCT source very far into the tissue. Imaging penetration, we're going to go into a definition in a minute, is how deep can you image, and let's say 3 millimeters. And so noise and noise-like things are going to play a big role in causing problems with this. Now, ironically, SS-OCT made it big because of cardiology, but in the eye, because the dynamic range is so, it's transparent and the dynamic range is so low between the maximum signal and the minimum signal, then in the eye, these may not be that important. And so for ophthalmologists, it's not clear if time domain would be that useful for ophthalmology. So here are definitions of dynamic range and signal to noise ratio. So I'm just going to simplify these definitions for people in physics or engineering. The definitions are there. So the signal to noise ratio, let's say that's the light, the maximum signal detected to the noise level. And we hope that noise level, and we're predominantly talking about the optical, is near the quantum noise limit, where quantum mechanics sets up a barrier. And again, that's going to be talked about in the quantum mechanics lecture. The dynamic range is what we get for this lecture on the screen after we digitize it. It's what we see in it. And so, do we see a difference? Yes, we've published this. And I'm not going to go into these different type of errors, but the references here, you can read about them. But so on the left, we image scaffolding that's used for tissue engineering with TD-OCT and SS-OCT, and tried to get all the parameters as close as possible. The power of the source, the bandwidth, everything as accurate as possible. And you see in the SS-OCT image, it's not as sharp. The different color arrows are different types of errors that are occurring in the signal. And so we've shown it from an experimental standpoint. Head to head, we have seen TD-OCT, if everything is optimized equally, being superior in terms of imaging quality, not speed, to SS-OCT. And so on the right, if you've ever worked with an SS-OCT or a system, you know that if you're out of focus, you get like a wraparound, like a fold over of the image on top of itself. And that doesn't happen with time domain. And it has to do with the mathematical conversion. So we're reconstruction, it's part of the reconstruction process. And it's inherent to these Fourier-based techniques. So penetration isn't how far photons get into the tissue. Penetration is how deep we can image structure, and it depends on the dynamic range, multiple scattering, which was explained in a previous lecture, resolution, which should be the same for both, and to a lesser degree, total power. Now, we have a problem with noise in SSOCT and spectral radar that's less of a problem in TD-OCT. So if we just take low frequency noises that are inherent to the electronics, all right, in TD-OCT, we have a way of getting around that that's not easy to do with the spectral techniques. So this shows, or hopefully it shows, so the initial signal coming in is Doppler shifted. So if we think the signal we want is in the middle line in the middle and we're at the top A, okay, we don't have our autocorrelation function, what we want to use to represent and put in our pixel yet. It's Doppler shifted. But the middle is low frequencies. So if we put a filter right in the middle, now it's been Doppler shifted by that moving mirror, positively and negatively. If we put a filter in there, we eliminate our low frequency noise from our let's say our electronics, okay? And then we can demodulate and log it. And that logging is very important before we go to A to D conversion, because let's say our A to D conversion is at best 80 decibels, but our original signal is 105 decibels. So by logging it, we can get it to the point where our A to D converter can convert the whole signal. But SSOCT sends the whole raw signal to a computer. Is going to be digitizing a lot of the noise. And so we're not going to see that. So you see here that after demodulation, you have the carrier frequency in B. And then you have our autocorrelation function. And then you just use a second filter that removes the Doppler shift. And we get a cleaner signal. Now, digitization is, so if we look at it's a little bit easier at first. Let's say we have Gaussian electronic impulse. So we can only quantize or digitize that a certain amount. It's not continuous. And so you send out that digital signal, and it depends on the number of bits you have, how much you digitize it. And so you can poorly digitize it like up on the top, or you can digitize it on the bottom. But as we already talked about, you can see digitization creates errors in it. So once we log that information, then, or Fourier transform it, then those become errors. So that's avoided in time domain OCT, but occurs with the spectral based OCT. And so there, again, this is covered a lot, and I'm going to give you references. In those chapters, the errors are large. And this is out of one of our papers comparing noise and things that artificially influence the signal between the three types, and the references there, and it's also covered in the book. Now I just wanted to add this reference. So this is a 2017 reference. They're going to go into more technical aspects. I don't really care about, how exactly you're sweeping the source, for instance, and I wouldn't write that in a book now, but the paper does, the Bohr has been around and successful for a long time. I don't know the other two authors, but they do give you early references, particularly between 2000 and 2005, where people worked on the optoelectronics, and they're more supportive, though I disagree with some portions of the paper. I believe there's far more North sources. But if you want to look at some of the work from other groups in developing the optoelectronics, then I included this reference. Now, the next couple of papers, this is where that chart came from. So we went through the theoretical and practical considerations of the modalities. And it's covered pretty extensively here. So if you do have a background in physics or in engineering, you have a paper, you could read it. I'm not going to cover it. And particularly, I painstakingly went through deriving from scratch all three embodiments. So right from the beginning, resolution and performance for the three. And strangely, some of the equations we had been using weren't completely correct. prior to that. And I'm not aware if anybody else has just completely derived out these embodiments. But in chapter 5, they're derived out completely in the textbook. Now, one thing we tried to do is, which we did do, we put a logarithmic amplifier inside the SS-OCT system, and it helped the performance, but it's not going to get us to where time domain is. And there's a series of papers, and I'm just going to go through these rapidly, and I'll tell you why I'm going through rapidly in a minute. So we went through, and you saw the scaffolding one where we just compared the modalities head to head. Finally, and we patented this, we developed a calibration system between the sweeping and the processing at the A to D converter. We put in a MZI clock. But by the way, I want to mention Bin Lu. I haven't mentioned him in the other ones. He was an instructor in my lab for several years. And so he did some great work. Isan was a student. Did some great work through the years, and I don't think I've recognized him in previous, very much in previous presentations. But one of the questions that in retrospect I asked her is, why did we even get into this? This isn't what we do. We were worked on perfecting SSOCT to try to get its performance up to the level of TD-OCT. Primarily, I think we did it because we wanted to demonstrate to people that it is worse than time domain OCT, and people just didn't seem to believe that. So, I mean, the conclusions are, right now, if you want speed, then it's the spectral domain techniques. Sorry about that. If you want performance, I believe it's time domain, and can time domain be brought up to very high acquisition rates? I don't know. But we'll just have to see in the future, but more work should really be done on time domain. Thank you.